Welcome back, guys. The same uh, companions from the last video, Mr. Jayesh Chahar and Mr. Kushagra Mittal. We talked about quite a few things in the last session. We talked about various classification metrics. We gave a lot of examples. If you remember the asteroid example, we had a good discussion on it, and it was pretty intuitive, and we took things from there. So it was more about classification, and we thought before moving on, like we promised to predictive maintenance and all, let's give you a hint of how to go about machine learning algorithms from scratch. If you are just starting with data science and you have a good understanding of various mathematical backgrounds, you might as well enjoy this lecture and take away very important machine learning algorithm from it. The idea behind machine learning is very simple. It's just that we are trying to create an artificial brain, and the input that a brain would require in that case is data, right? For example, a child is born, he looks at various kind of things in the world, and his brain keeps on developing and keeps on understanding more and more things. And by the time he or she is 25 or 30 years of age, he becomes smart in some way or the other. The reason he or she is smart is because all over the 365 multiplied by 25 days his or her life, he has taken as inputs various forms of data. He has listened to noises, he has looked at images, and the brain is capturing all of it. And the brain is what we call in machine learning terms, the brain is training itself. So whenever something new happens, based on how the brain has trained in the past 25 years, something new, the brain does not find difficulty in doing it. But for example, things like things which are very new. For example, suppose I had never met Kushagra and I see him the first time, I will be like very numb because I don't know him. He's a total stranger to me. But I have met Jayesh plenty of times because he was my batchmate. So if I meet him, my brain will respond fairly better because my brain has trained to understand that Jayesh is a friend. Okay. The reality is Kushagra is also a friend, but just an example. So that's how the brain goes, and that's how machine learning goes as well. The data, the kind of data the machine trains on, if the same kind of data comes in the future, then the brain does good performance. But if some totally awkward kind of, suppose an alien stands and comes and stands in front of you, your brain will be like, oh god, what's up, because it has never seen, it does not know how to react. So that is a totally it's called an anomaly in data science terms. So data driven models, they don't perform well on anomalistic data sets, right? So you have to make sure you understand that, like the brain, even a machine learning model is as good as the data it has trained on. Okay, so I'll stop with my TED talk here. I will move on to more practical version of things. I will explain a project, a simple project. I promise it is very simple and it will do justice to the term linear regression from scratch. I'm afraid my dear friends who are in this session with me today will not be able to speak much because it will be a project based sessions. I will invite them for their doubts and all so that we can have a discussion later on. So I'll directly jump on to a project with linear regression, and I'll take 2 minutes to share my screen.
Hey guys, while we're waiting, I think it would be good if you could slightly explain what linear regression actually is for those of you, for those people who don't know.
Yeah, exactly. Actually, linear regression is the most simple algorithm of machine learning. Simple but powerful. So in linear regression, we attempt to model the relationship between variables and label in by feeding a linear equation between them. For example, remember in your childhood days while we were studying coordinate geometry, 2 points were given, 2 points with its coordinates were given to you, and you were asked to join the line between them. So joining that line between two lines, that was kind of a linear regression, and finding the value of y in between the two axes of the given point. It is type of a machine learning algorithm itself. So this is, you can say that we can define linear regression in layman term, that joining two lines in our childhood days was a linear regression. So further discussion by the answer, sir.
Yes, I'm glad Jayesh you brought the coordinate geometry part up because the concept of straight lines from school is exactly what we are starting with today. I will connect your prior learning with a new concept. You'll feel like you have already learned this in high school. You are just doing it in Python today. Okay. And you will be highly motivated at the end of this lecture that machine learning is pretty much easy. Like you'll get the whole feel of it. And trust me, even if you do, various difficult algorithms or maybe fancy algorithms like neural networks and all in the future, you can still pretty much relate the feel of things, the algorithm, the stepwise workflow with what linear regression does. So the best part is in various machine learning algorithms, the core, the stepwise workflow, it kind of remains the same. Some algorithms might have additional steps as per their requirements. Some algorithms might have lesser steps, but the truth is, all of them, if kept in parallel, they kind of look similar in the workflow. Okay, so let's start with what Jayesh told us. So just imagine you have a lot of, suppose 2 points are given, right? One point is here and one point is here. Then you connect a line between those 2 points based on your understanding of your coordinate geometry and stuff. And now you know that just based on these 2 points of data, you have created a model which is this line in between. And this model, if you know the equation of this line, you can predict basically any, if you have new x, you can predict new y. Even if you just started with 2 data points, now you can use the straight line equation and make predictions for infinitely many data points. That's exactly what
Yeah, you
you
can
are.
imagine it like extrapolating the line.
Exactly, exactly. So you can just because you know just these 2 points, even in the points in the interpolation of these two lines are new to us, even in the extrapolation of these 2 points are new to us. But if you know the straight line equation, you can find out y for each and every x along this horizon. So that's the concept of machine learning. Your brain has done it because you know that 2 points will convert to a straight line. How to do it in machine, how to train the machine to do it is the target for today, right? So what we will do today is we will write a program that we will start with a straight line equation. First step, we know the equation, okay? Then we will generate data from that equation. Okay, this is more like a verification of does machine learning actually do what it promises, right? So we generate random data from that straight line equation that follow that straight line equation. Okay, so the straight line equation I'm going with today is y equals to 2x minus 3. Simple mx plus c kind. And you can, at your homes, you can try different sorts of equations, right? I will share the link to this GitHub. I will share this code in GitHub and share the link as a part of the section in the video later on. But we start with y equals to 2x minus 3. I will generate data from this straight line. So we will have plenty of data points that follow this particular rule. Now we feed these data points to a machine learning algorithm, which is pre-built in what is called the scikit-learn package in Python. That's a very popular Python package. It has sklearn. Sklearn is very popular. It has a lot of machine learning packages already coded. You don't have to code it explicitly. If in case you need a tutorial on how to code a machine learning regression problem explicitly, please write in the comment section of the video so we can devise a separate tutorial for that. But today's tutorial is more practical and less code heavy. So we have x comma y points that follow this particular equation. So if I can just show you the data that, so this is the data I've added. I have to match it with practicality. I have added a random noise to it as well. I will tell you how to do it. So this is the data that follows that equation, y equals to 2x minus 3, right? Now, the task is to fit a model. Now your brain has already imagined a model that passes through this, because there is a clear trend and slope and all that in this particular picture that you see. But can the machine do it? That's the task. So our target is to first understand, to feed this data to the machine. The machine will fit a model to it and kind of do a straight line fitting. That's the ideal requirement that we want from our algorithm. Finally, we call that training is successful if the machine successfully fits a straight line in between. Then we are not stopping there yet, because this is the data that the machine has already seen. Now we have to validate the model's performance on data that the machine has never seen, right? So that we do by creating new sets of data and using the same trained model. We call it now a trained model. We have created a brain that understands this relationship. We use that brain on new x to find new y, and then we try to plot them again. If the plotting shows the results pretty well, then we can trust this model and we can say that now the equation 2x minus 3, I also have a machine learning model that understands 2x minus 3, right? And further, finally, when we will check for the slope and the intercept of that machine learning model, we will find out that that model pretty much understands all of it, right? Uh, I see.
Yeah, here actually I want to add a point.
Yeah, I just a
As you can
second,
see,
just a second. I guess Mukul Goyal will wants to join the room, so we will admit him, right? He is waiting. Yeah. So we will just introduce. I'll just introduce Mukul. You are on YouTube
yeah,
video recording. Welcome to the session. So we are halfway through the discussion about linear regression from scratch. So I'll introduce Mukul. He's a petroleum engineer turned
wonderful.
data scientist. He has a very nice experience and pretty advanced experience in data science. He has a startup of his own as well. He's been working. He has, I guess, almost close to 2 years of work experience as well. And he's doing great things in data science and machine learning. So welcome, Mukul. If you
Hello
want to
everyone.
just,
Sorry for being late. I was in another meeting.
yeah, I totally understand. Can you please, like, 1 minute you can take and say something about
Yeah,
yourself?
sure. So I graduated from University of UPES, Dehradun, just like Jayesh and Kushak. And then I joined Wipro as their campus recruit in their ENU domain, where I'm working in their data transformation and data management processes for one of the UK international oil and gas majors. And I'm also working as a founding data scientist in a startup called Monkey, which is striving to solve mental health problems using more of a data-backed insight and getting uh, get bringing streamline into the process on how we currently do the diagnosis and improving the accuracy of the diagnosis. So at Monkey, my work involves developing data pipelines, maintaining those, and also developing models based on the data that we gather, and maintaining dashboard for the clinicians to watch for their patients and those things. Apart from that, apart from, so this is basically all about me. I'm also learning. So my current interest includes ML operations, where I am trying to understand how machine learning integrates with current software engineering architecture, and how we can bring machine learning from Jupyter notebooks to production using different cloud environments.
Great. Thanks for that introduction, Mukul. Something to learn, pretty advanced. So I'm sure he will take this revision and enjoy this, because we are building
Yeah,
him from
sure,
scratch right
Dinesh.
now. Yeah. So let's move. So Mukul, just to update you up, I'm doing a regression problem from scratch where I'm creating synthetic data and training a machine to understand it for our audience. So yeah.
Okay.
So coming back to the discussion. So we had already created this data. The ideal thing would be to train a machine to understand this data, to fit a model, and then validate the performance on the new model, new data. And if that works well, we check for the coefficients. And in this case, since we are creating data from an equation that we already know, the coefficients and the intercept, if we find out from the machine learning model, we can verify that if the machine has actually understood this data or not. So that's the end goal of this product. So let's start with the step-by-step approach. So in machine learning and data science, these are the libraries that you will pretty much find: NumPy, Pandas, and Matplotlib for plotting. NumPy and Pandas are basically for data operations and mathematics, more like calculation specific and data processing libraries. NP is the alias, like it's the other name for NumPy, because we cannot keep on writing NumPy anymore. You can watch other tutorials on our channel to understand what these libraries do. So now, after we have imported, we will need sklearn in the later section of this video, but let's go step by step. So this is the equation that I am assuming that this is some sort of important equation for me, and I also have the data which I'll basically create. But normally in practical scenarios, you have in oil and gas reservoir engineering, let's say you have, let's say, porosity permeability data. Everyone knows there is a physical relationship between porosity and permeability, right? In that case, you might not know the actual correlation. So what you have, 10,000s or millions of data points, that evidence is enough. If you don't know the equation, even million data points are enough to fit a correlation. But since this is a scenario we are creating for understanding, we can assume an equation, create data from it, fit a model, and create coefficients from the model and verify if the coefficients are the same as this, right? So first up, I've created a function that takes two inputs. One input is the number of data points that you want to create. Basically, we will be creating training points and testing points or validation points. And this is the second parameter, is the error that you want to provide, because we want to match this scenario with practical experience. Error is important because if I just provide zero error, you'll find out that it is just dot 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 in a straight line. That is very easy to train even if you don't have a machine learning model. You can do that in Microsoft Excel. So what is the use of machine? So this is a more like a challenge to the machine. Higher the error point that you provide, the data will be more scattered. I'll just show you an example. So uh, yeah, so
So this error would be the noise in the data,
yeah,
right?
yeah, you can call it noise. You can see after I've created data from this, so I've created a NumPy array. You can see linearly spaced data points between -1 and 1. Number of data points are exactly what the user provides. Then I'm using this equation that I've assumed to create the y. So basically, x is the input, y is the output. I've created the data. Now this, by this point, if you plot this data, it will be a very straight line of scatter points, right? But it's not practical. You will never find such data. It's very ideal. So what you do is you create an error array of error can be like, this is the way to create error. You're basically asking how much error do you want. Suppose I provide the magnitude 2.0, you multiply it by 2.0, it magnifies the error, it scatters more. If you give 5, it even scatters it more. The higher the error, the difficult it becomes for a machine to train on it. You can do that hidden trial by yourself. This is one challenge that brings forward to our notice that data quality is very important. Okay? So suppose I provide an error of 20 in this, and if I try to train, I provide 100 data points with an error magnitude of 20. It will be terrible. I'm definitely sure it won't fit a model as well as we are going to see. You can try this at your homes. So that's a very important challenge. Like, data quality is very important if you are trying to train a model.
Also, I think I would like to add is
Sure.
there's one thing where data processing comes into play, where you are trying to process the data in a way that you are trying to remove outliers. You are trying to do a simple statistical test on data uh, to identify outliers, handle outliers, and uh, just remove them from data, or how to treat them, basically.
Exactly. Exactly. Yeah. So suppose, like, we take that point that Mukul just put up. Suppose we only have the data with, let's say, 20 magnitude of error. In this case, it will be very scattered. Now, what to do? Do you actually have, if you have to do something, you have to apply data processing in that scenarios. apply some sort of scaling or something to bring to narrow down the range, to bring the data points closer from 0 to 1 maybe, or -1 to 1. There are two kinds of scaling options available. So basically, in cases where the data is very shitty, you always have to provide some sort of pre-processing step. That's a very important pipeline in data science workflows. Data pre-processing is where, I'm sure all my panel members would agree, we spend most of the time in our machine learning algorithms. So that's not shown in this project because it's like the pretty much the first project. So yeah, we'll definitely do a
Also,
video on that. Yeah, yeah,
one more
sure.
thing I would like to add is whatever the data processing step you have taken with training data, that needs to be also done with the prediction test data or the validation data that you are testing the model on, and also on the future data that we'll be taking the prediction on. Because if you do not, because basically that is a concept of the where the concept of the data drift comes. So the
Exactly.
distribution of the data that you have trained the model on and the distribution of the data that you are taking the prediction on is different, than the model will not give accurate predictions. The distribution should needs to be same for the data that you have doing the training, and for the data that you have taken the prediction on.
Exactly. To correlate it to a real life example, suppose my brain has a particular issue that I can only remember or recall a person if he's wearing white clothes. Okay. So I know Jayesh because from my past, I know Jayesh in white clothes. If he wears pink clothes, I won't be able to remember or recall him. So this is some sort of requirement. I need to pre-process Jayesh to make him wear white clothes first so that now I can understand. If Jayesh comes to me without white clothes, I cannot remember who he is. So for data as well, you need to understand, like you need to understand how the machine has trained in the past, use that understanding to apply that understanding to the data in the future, like the new data. And exactly, very important point. Processing on training must be applied to processing on testing as well. So moving forward, so this function is pretty much clear. It returns x comma y. X is nothing but a 1D array between -1 to 1, and y is the corresponding y points that follow this rule. Of course, some noise is added. So this is the function that we have in our hand. Then suppose we create 500 data points with an error magnitude of 0.2. Now there's this important step in machine learning. You always have to make sure that the feature array X is basically the norm for a feature. In this case, our feature is one dimensional, but that will not always be the case. Our features will be multiple in a lot of scenarios. For example, the equation might look like 2x1 minus 3x2 plus 5. In that case, we have x1 and x2, two features. In that case, one our 2D plotting will not work. We have to use 3D plotting. So that can be that is there. So it has to be ensured that X is always 2D. So currently I'm returning a 1D array. So the shape will be 500 comma. So we have to convert it to a 2D array first, right? And then we just basically plot it. Now I'll just come back to the point I just told you. Suppose I provide the error magnitude as 10, right? And just I plot it again. You can see it pretty much tells us that you cannot fit a model into this data. But if I
Data is not
provide
linear now.
exactly, now the data becomes havoc, like totally bullshit. Like you cannot do something with it. So now if
And
you
here
provide
I want to add a point that the importance of exploratory data analysis, you can see from here that we have a data set of X and Y. The first step will be we should visualize how our data is present.
yeah,
In the previous case, the noise was very less and it was kind of a linear type of presence. So in my mind, it will come, okay, it is linear kind of data. So I should use linear regression. So I get good results in a less amount of time. So the exploratory data analysis also help in this thing that to select which algorithm we should use and understanding the data more and more.
exactly, exactly. So suppose we ignore Jayesh's point and we just go on and fit the machine learning model directly, this data, and we fit it into a linear model. We might not even know that, we might not even know what's going on, what's wrong with my model. I'm fitting a linear model into a data which is not linear. or which is horrendous. Like it has a lot of errors. So exploratory data analysis is there to help you in these cases. You visualize data to understand what kind of data it is, so that you pick up your strategy accordingly. Now, if this was my data, I would go with different approaches, maybe no approaches at all. But if now I'm reducing the error magnitude, if this was my data, now I can clearly find out by just looking at it, exploring the data, analyzing. That's what you call EDA. I can understand there's a linear trend, there's an intercept, linear regression is fit for this model, right? Now I can move ahead and go on with machine learning. I can see that data is pretty fine. Everything is sorted. Now I can move to the machine learning training part, right? Now what we have in our hands, we have X train and Y train. That is, we have X axis for the training section, and we have the Y corresponding Y axis for the training data. Now we use these data sets. These are the data that we show to the model. We expose this data to the machine, right? And we will further check the machine on the data that it has never seen, right? So this is the way to import a pre-coded linear regression model from scikit-learn package, right? So there is a class in scikit-learn called linear model. We import the linear regression class. So there is this is the way to import the linear regression class from scikit-learn. So here it is. Then we instantiate a model. This is the way to do it. This is more like storing the model utilities in a particular variable, which you can use to call for various activities in the future. Very simple. You will do this for every class. So this is the way. In this bracket right now, we don't have the time to discuss it, but in this bracket is something that you will use in the advanced projects. It's called hyperparameter fitting. Like you can provide various parameters that will enhance your model performance in a way. Surely we will discuss this someday in the future. Now is the main part. Model.fit x train comma y train. Model.fit input data comma corresponding output labels. That's what you give to the model and you run it. So your machine has now trained on, once you see this output, it means that the machine has now trained on the X train comma Y train data. Now we have to check by plotting or by various error metrics. In this case, I'm just plotting. We will make model predictions. So this is the way to make model predictions, right? So I'm doing a scatter plot just like I did in two code steps back, X train comma Y train, which is the actual data. And in the second step, I'm plotting the model predicted data, right? So this is the result. You can see the blue dots are the actual data that you just saw, and the red line is the model predicted data, right? And you can see the machine learning. So blue is what you are providing to the model or the machine. Red is what the machine says that this is what I have understood from the data that you gave me. So you can pretty much see that the machine is doing pretty well. But you cannot just blindly trust the model at this point, because this is the data that you gave to the machine. You expose this data. Maybe the machine has memorized it. Memorizing is not understanding. So you have to check this machine's performance on unseen data. So now we create the unseen data using the same function. Now, since this is a random data generation kind of function, we will find out that new data points we are creating, 50 data points we are creating with the same error magnitude, which is kind of similar to saying that the same processing is applied, right? Same kind of data as the training data, right? Now we are applying this again, the same step, creating it to a 2D array. Now we are asking the model to predict Y for this new data, and then we will validate this Y with the actual Y, right? So this is the result. You can pretty much see that on data that the machine has never seen, the red line still fits that data, given the data follows the same physical rule, that is 2x minus 3, on which the machine trained on. So when people in petroleum engineering, they say that machine can understand physics, that's my answer to verify that concept. Because suppose 2x minus 3 was some physical rule of which we had the data. Now the machine can understand that physical rule, and that's the evidence of it. If you still don't believe it, we can fetch this red line's coefficient and intercept, and that's what I have done. You can see the coefficient is 1.96 and the intercept is minus 2.98. 2x minus 3, guys. 2x minus 3. 2x minus 3. The coefficient is 2 in actuality. The model's answer to the coefficient is 1.96. The intercept was minus 3 in actuality. And what the model's intercept is minus 2.9. So now we are sure enough by various layers of validation, we can say that this machine learning regression model is smarter. So that's about it. Any discussion? We are short on time, I guess 2-3 minutes remaining. So
Yeah, actually,
yeah,
we just made our machine to understand the physics behind certain data. You just provide the data to the machine, and it will automatically search the pattern in it and learn the physics by itself. You don't need to code anything about the physics or anything about the equation. You just need to know how to handle data and how to get your model trained.
exactly. What Jayesh is saying is, suppose we didn't have this function, all we had is directly we had this data, and we applied exploratory data analysis. We understood that this is some sort of linear relationship. We don't know whether the intercept is 2 minus 3 or whatever. All we have is that this is a linear trend. Then we fit it and we find out the model coefficients and all. Now from data we have devised a particular equation, and given that we already knew, we can verify that the performance was fair. Like we can trust it in physical scenarios. If we have 10,000 million points, huge data set, it's more than enough as an evidence. For example, Timur's correlation. There was a project I did on Timur's correlation, which is a very popular porosity permeability correlation in oil and gas. It follows the reservoir physics. So we have, suppose from a reservoir, we have, let's say, 50 million data points from that reservoir, and we know the actual physics is Timur's correlation. We don't need to remember the Timur's correlation. We can use the data from that reservoir, fit the data in a model, make the model understand the data. Now we have a working model that understands the correlation. Suppose Timur's correlation was developed in some other part of the globe, and we are working in Barmer, where this correlation maybe does not hold true. Then we can make use of the advantage machine provides us. Machine learning will help you devise a state of the art in situ correlation. You know, we don't have to depend on predefined correlations anymore. We can devise the correlations that understand the physics from the data without assuming anything. So on that note, I guess we will continue this discussion with more advanced scenarios from the next session. So great having you guys. Thanks Mukul, thanks Jayesh,
Just
thanks
one
Kushal.
more thing I would like
Sure,
to
sure,
add.
sure.
It was a very good discussion by Vivanshu. You have like given some real world examples and explaining that. So just one more thing, as the one who will be watching this podcast, as the exercise you can try having changing the error in the test set and see if the data distribution changes, then the line will not fit into the model. So that can be the one exercise that they can do on and learn more about how data distribution and how managing the data is also important. It's not all about managing the model, it's all about managing the data.
Great, great exercise. Yeah, definitely do try this. Play around with error and see how your model fails. Try 1,000 things to fail this model, and you will understand a lot of things in that. So thanks Mukul for that. Definitely people
Sure.
will practice
Yeah,
that.
yeah. Also, you can try to apply removal, as
Yeah.
Mukul said. Okay.
Okay, we are
Thank
out
Thank
of
you,
you.
time, I
everyone.
guess.
It was a
Thanks
great
a lot.
discussion.
Thanks a lot. Great discussion. See you again.
Thank you. Bye.
Cheers. Bye.
Bye.